and now we will welcome Professor Jason Smith from the University of Oxford in the UK. And the title of his talk is Engineering Qubits in Diamond for Scalable Quantum Technologies. Jason?
Hello, this talk is entitled Engineering Qubits in Diamond for Scalable Quantum Technologies. And it focuses on some work that we've been doing in the last few years in Oxford on the laser writing of nitrogen vacancy defects in diamond. So this image that you can see here is a fluorescence image of a piece of diamond. You can see the scale bar of 1 micrometer here on the right. And each of the bright points that you can see is fluorescence from a single nitrogen vacancy defect in the diamond. So this is a little bit like the images that we're used to of the fluorescence of individual ions in an ion trap, except this time we're looking at fluorescence from individual nitrogen vacancy defects which have been permanently written into the diamond lattice. So I'll start the talk with a bit of an introduction to NV centers with some motivation and some of the generalities of the creation of NV centers in diamond. And then I'll describe the 2 variants of the laser writing method that we've developed. First of all, using the laser to write vacancies, and then using a thermal anneal to create the NV centers. And secondly, to use the laser also for annealing the diamond, and the use of feedback control to achieve deterministic fabrication of NV centers. And at the end of the talk, I will describe some of the recent work that we've been doing on simulation and modeling of the NV fabrication process to better understand what's going on. So much of the promise of NV centers for scalable quantum technologies is that they provide a spin-photon interface so that you can optically address electronic spin states and nuclear spin states in the diamond lattice. So the electron spin of the NV center couples to nearby nuclei via the hyperfine interaction, and this allows the optical initialization and readout of individual nuclear spin states. Now, perhaps the most beautiful example of this that's been published so far is this work by the Terminiau group in Delft, where they've demonstrated that they can create entangled states which involve up to 10 spins around a single NV center. So including the electron spin on the NV, the nitrogen-14 spin from the nitrogen of which the NV is comprised, and an additional 8 carbon-13 spins in the surrounding diamond lattice. And they've shown that using dynamic decoupling techniques, you can preserve the coherence of quantum states on a single nuclear spin for up to 70 seconds, and on entangled nuclear spin states for several seconds. So this provides a basis for envisaging devices in which arrays of NV centers are written into a chip. Each NV center corresponds to an interface with a node consisting of multiple nuclear spins, and those nodes can be entangled together via a photon-mediated entanglement of the NV electron spin using some optical multiplexer. So we can entangle together arbitrary pairs of nodes on our chip by controlling our beam steering and our optical multiplexer. So if we think about the physical dimensions involved, we can easily envisage a separation of NV centers or of nodes on this chip of around 10 micrometers or so. And this is primarily limited by the optical interface and the need to put electrodes around each node. So this would give us a node density of 10 to the 6 to 10 to the 8 or so per square centimeter. Now, for the optical entanglement between NV centers, one would need to cool the chip to 4 Kelvin to get narrow optical transitions that would enable you to generate that entanglement. But these days, this can be achieved with relatively straightforward, almost benchtop cryogenic systems. So now let's turn our attention to the formation mechanism of NV centers in the diamond lattice. To create an NV center, you need three main ingredients. You need a source of nitrogen, which can be grown in during the CVD process, or can be implanted into the diamond after the crystal has been grown. You then need a source of vacancies, and you can create vacancies during ion implantation. You can create vacancies via irradiation with a high energy electron beam, or you can write vacancies into the lattice with a pulse laser. Thirdly, you need to anneal the diamond. You need to apply heat to increase the local temperature to above 850 degrees centigrade, and this will activate the diffusion of the vacancies so that they can move around in the diamond lattice. And when a vacancy finds a substitutional nitrogen, it will bind to it and form a stable NV complex. The two methods that have traditionally been used for generation of NV centers in diamond are ion implantation and electron beam irradiation. And the challenge here really is to achieve precise positioning of the NV centers and at the same time to minimize residual damage to the lattice so that the NV centers you create have good coherence properties. So for ion implantation, the positioning accuracy in the lateral direction is achieved by implanting through nano apertures, and this can give you 10 to 20 nanometers or so positioning accuracy. And the depth positioning is achieved by tuning the energy of the ions during implantation. Now, the caveat with high energy implantation is that you create a lot of residual damage, which is difficult to then remove during an annealing process. Electron beam irradiation, on the other hand, is a gentler process that creates less residual damage. To achieve the lateral positioning accuracy, you can use a focused electron beam, such as in a TEM, and for the depth positioning, you can delta dope your diamond with nitrogen. Now, both of these processes, however, are inherently stochastic, so the annealing step of NV formation is applied to the entire diamond crystal, and so essentially you can target a particular average number of NVs that you want to create per processing site, but you can't deterministically create a selected number of NVs per site. So in our first work on laser writing of NV centers, we started just by applying single laser pulses to sites in an array and varying the energy of the laser pulse so that we could establish the dependence of the laser pulse energy on the formation of defects. And you can see here in this image on the left, this is a fluorescence image of an array of sites that we've processed. And at the bottom of the image, we have a low pulse energy for our laser, about 20 nanojoules. And at the top of the image, we've gone up to a much higher pulse energy of about 62 nanojoules. And this image was taken immediately after the laser processing had been done, before any annealing had been done. And what we can see is that above a certain threshold energy labeled E1 here, we can start to see fluorescence from the vacancies which have been created by the high energy single laser pulse. And the neutral vacancy has a characteristic spectrum, which we label here as GR1, with a peak at about 740 nanometers. As we go to higher pulse energies, towards the top of the figure here, we see additional broadband fluorescence at slightly longer wavelength. This is B-band fluorescence, which comes from additional damage of more complex defects in the diamond lattice. So we can see here that these higher pulse energies create more damage, which is not just individual vacancies. When we anneal the diamond, we find that the vacancy fluorescence disappears, so we don't see the GR1 signature anymore. And this occurs because most of the vacancies will recombine with interstitials, which are also formed during the laser writing process. Now, in place of that GR1 fluorescence, we see fluorescence corresponding to the negatively charged NV defect, this NV minus spectrum here on the right. And we can see evidence that we are creating individual NV defects, because in some sites, especially at the bottom of the figure here, which is in a region below where we were able to see the GR1 fluorescence on the previous slide, we can see sites where no fluorescence occurs, so no NV has been created, and sites where we see fluorescence from an NV center. If we go to the very high pulse energies, we find that the annealing stage does not restore the diamond lattice and create NV minus, but rather graphitizes and creates this B-band fluorescence signature that we see above this green line here. So if we focus our attention on the NV centers that we've created at these lower pulse energies and perform spectroscopy of our NV center at low temperature, so perform measurements at liquid helium temperatures, we can see examples of very narrow optical transitions from the zero phonon line of the NV center. And this is one of the best examples that we measured. You can see the spectrum of the zero phonon line, and you can see the photoluminescence decay from the same NV center. And what we find is that the line width from the spectrum corresponds very closely to the T1 time, the photoluminescence decay time that we see in the time-resolved data. If we look at the correspondence between this line width and this decay time, we can establish that the pure dephasing time, the T2 primed, is many times bigger than the T1 time that we've measured from our fluorescence decay. So this is an example of a highly coherent optical transition that would be very, very good for performing photon-mediated entanglement between NV centers. If we put together some statistics for a large number of NV centers, we see that not all of them show such good performance as this. We see that we're more likely to get these highly coherent optical transitions at the lower pulse energies. As we turn up the pulse energy, we start to see a sort of systematic broadening of these optical transitions, which presumably comes from an increased amount of damage in the diamond lattice that is not annealed away during that annealing stage. So a lot of our attention at the moment is focused on developing the method and improving the method so that we can generate a higher yield of highly coherent NV centers in terms of their optical transitions. When we look at the spin coherence of the electron spin of our NV center at 300 Kelvin, we find that the T2 time, as measured using a Hahn echo measurement, is several hundred microseconds. And this is likely to be limited not by the damage in the lattice, but by the nuclear spin bath, the carbon-13 nuclear spin bath, which creates a slowly varying magnetic field, which causes decoherence of the electron spin. So the T2 times that we're measuring here are comparable with those which you would normally expect to see for NVs which are grown into CVD diamond, so high chemical purity CVD diamond, but with a natural concentration of carbon-13 isotopes, which is about 1%. So we should be able to increase these coherence times, these T2 times, by writing into isotopically purified diamond material. So the next step of our work in an effort to achieve greater control over the writing of individual sites was to introduce the laser annealing of the diamond, as well as using the laser to create the vacancies in the first place. So here you can see we have our Ti-Sapphire laser fabrication beam. We use a spatial light modulator so that we can compensate for aberrations and make our focal spot as small as possible. And we have 250 femtosecond pulses with a 1 kilohertz pulse stream, which we will use for the annealing process. In addition, we build onto our writing microscope a basic fluorescence microscope so that we can excite at 532 nanometers and measure fluorescence using a single photon detector. And this will allow us to watch for fluorescence appearing as we're performing the annealing step in our diamond. So this video illustrates what's happening during this process. In the diamond lattice, we have some nitrogen, and so this is quite highly doped with nitrogen to about 2 parts per million. And then we apply our first high energy laser pulse to create vacancies. And this actually creates Frenkel defects, so it creates vacancies, but also creates interstitial carbon atoms. And then we turn down the laser pulse energy and apply this 1 kilohertz stream of lower energy annealing pulses. And this just puts enough energy into the diamond lattice to gently anneal the diamond and mobilize both the interstitials and the vacancies, some of which will recombine with each other, but then eventually a vacancy is likely to find a nitrogen and form a stable NV complex. And this is what we see on our monitor during this process. When we apply the seed pulse, we don't see any fluorescence appear then. But when we start applying our annealing pulses, we start to see intermittent fluorescence from an NV center. And this continues for a few seconds until after a while, the fluorescence comes on and stays on and is nice and stable. So this allows us to turn off the diffusion when we see a stable NV fluorescence to make sure that we have a single NV center. And the result is arrays of single NV centers like this one shown here on the left, where we've processed 25 sites, and 24 of these sites we've verified to have individual NV centers. The verification process is with some Hanbury-Brown twist measurements to measure the photon autocorrelation function, and we see this anti-bunching effect. We see this dip in the autocorrelation function at a time delay of 0, and if that's low enough, that verifies to us that that corresponds to a single NV center. So this has given us a yield of about 96% or so for the creation of single NVs on demand in our diamond. And if we do careful measurements of the centers of those fluorescence spots that we measure using our microscope, we can establish the localization accuracy of the individual NV centers relative to the targeted points on the sites. And what we find is that the amount of scatter is less than about 100 nanometers or so in the XY plane. And in the Z direction along the optical axis, the half width, half maximum is about 200 nanometers. So this standard deviation that we see in the XY plane based on a best fit from a two-dimensional Gaussian distribution, this is about 39 nanometers, and this is much, much better than one would expect based on the diffraction limited spot of your microscope. Now, the reason for this is that the laser interaction with the diamond is highly nonlinear, and so multiple photons are required to be absorbed and to excite the carriers in the diamond in order to be able to create an NV center. And this high nonlinearity gives you a spatial resolution which is much better, much higher than that of your original microscope. So in the last few minutes, I would like to tell you about some of the simulation work that we've been doing recently to help us understand the laser writing process. There are two bits that I'd like to describe. The first is a finite difference time domain model of the laser pulse interaction with the diamond lattice. So this is a model in which we have a set of coupled nonlinear rate equations in which we're modeling the excitation of carriers within the diamond as a result of the laser pulse. We involve a number of different physical processes within this. So we're looking at the generation of carriers by multiphoton ionization and tunneling processes. We're looking at free carrier absorption to generate hot carriers, and then the subsequent relaxation of those carriers via recombination processes and by scattering processes. And we're also looking at the spatial diffusion of carriers in the diamond. So all of these processes come together in these coupled rate equations. And what these do is that they provide us with a picture of the spatial, energetic, and time distribution of the carriers within the diamond lattice. Now, what we're trying to do here is to ascertain the number of carriers which are generated and have enough energy that they can relax and create Frankel defects. And the activation energy for Frankel defect formation is between 20 and 30 electron volts. So if that's going to be created by a single relaxation event, we have to be involving very hot carriers in this process. So the results that we get, we can compare with some of our experimental data. On the left here in orange, you can see the predictions for the pulse energy dependence of the number of vacancies which are going to be created in our diamond. And in the blue, you can see experimental data for the intensity of the fluorescence from GR1 as a function of pulse energy. And you can see there's a very good match between these two graphs. Now, we've only used two fitting parameters for the simulation data, and that is the scaling of the two axes. The scaling of the x-axis corresponds to losses in our optical system, and the scaling of the y-axis corresponds to essentially the quantum efficiency of the fluorescence of the GR1 defects, which is an unknown quantity. On the right-hand side, we can see a comparison of the spatial distribution for the defect creation. So the color scale is the simulated result for the spatial distribution of the vacancies, and we're comparing that with the measured scatter in the position of the NV centers that we saw in the previous slide. So again, here you can see quite a good correspondence between the predictions and the experimental data for these spatial distributions. The second simulations that we're doing are to try to understand the way that the defects will behave within the diamond lattice. So we're performing density functional theory simulations of complexes involving nitrogen vacancy defect and interstitial carbons. And we're working out the band structure of these different configurations and looking at the spatial orbitals which are generated by electronic energy levels within the band gap that we find. So here you can see an example of a band structure calculated using our density functional theory for our NV center, which is isolated within the diamond lattice. You can see the A and the EXY orbitals here. And for the interstitial carbon, again, we can see these EXY orbitals based on these lobes from the split interstitial. Right, so these are for the isolated defects. So what we do is we're putting these together and performing simulations of different configurations, and we're looking for hybridization between the orbitals. And our hypothesis is that the blinking effect that we observe before the formation of the stable NV fluorescence comes as a result of hybridization between mobile interstitial carbons, which are diffusing around the NV center and causing varying degrees of quenching of the NV fluorescence via the introduction of non-radiative relaxation pathways. So we've simulated a bunch of different configurations, and this is the first example of what we can see. This is the configuration in the middle here, where we've got our NV defect and our interstitial carbon. If we look at the band structure that results from that and pick out the energy levels that correspond to the NV center, we can see a little bit of perturbation, but there's very little hybridization that occurs between the orbitals. And similarly with the interstitial carbon orbitals, we see a splitting, but we don't see hybridization of the orbitals. So we would hypothesize that this would give us a configuration where the NV center fluoresces more or less as usual. By comparison, if we have this configuration, slightly different, we find that we have a strong degree of hybridization when we look at the orbitals associated with the NV center and the interstitial carbon. So this configuration, we would expect to quench the NV fluorescence because of this hybridization. So when we bring this all together, we can put together a map of all the different configurations which give us this hybridization. And what's shown here is the map relative to the NV center. So the NV center is in the middle here with the nitrogen at the bottom and the vacancy at the top. And an interesting pattern emerges for the different positions and orientations of the interstitial carbon that give hybridization. If we're very close to the NV center, then almost any position or orientation of our interstitial carbon can cause hybridization. But as we go further away, it's only the positions of the interstitial which are closer to the vacancy than to the nitrogen, which give us hybridization. And we only tend to see hybridization when the interstitial carbon is oriented to point towards the NV center. So this is an interesting result. It could be because of the screening effect of the orbitals of the NV center due to the electrons on the nitrogen. But in terms of what's actually happening in the experiment and the blinking that we see before the fluorescence occurs, this could explain that particular phenomenon, because if you imagine you have one or a few interstitial carbons which are diffusing around in this space around the NV center, this would naturally introduce a modulation, a blinking effect of the fluorescence. So I'd like to finish by thanking the people who have been involved in this work. The early work on the laser writing was led by Larry Chen, and that was then picked up by Ben Griffiths with help from Lai Weng. And Ben has also been responsible for this rate equation model of the laser diamond interaction. Andrew Kirkpatrick and Guangzhou Chen have led the work on the density functional theory, and Colin Stevenon, Yashna Lekai and Ben Green and Gavin Morley at Warwick have done the T2 measurements. Colleagues at Strathclyde, Melbourne, De Beers and Element 6 have also been involved in various aspects of the work. And I'd particularly like to thank Martin Booth and Patrick Salter, who bring all the expertise and equipment for the laser writing processing. Funding has come from EPSRC, primarily through the NKIT program and the Quantum Computing Simulation Hub within the UK Quantum Technologies program. And we've also had student support from the Diamond Science and Technology Centre for Doctoral Training. So with that, I would like to thank you for your attention.
Hi, Jason.
Hello, Pascal.
Thank you for this very beautiful talk. It's very impressive what you can do with your laser annealing to create NVs. We have few minutes and a lot of questions, so let's be efficient. The first is it a problem for the coherence to need a high density of nitrogen to start with in diamond?
For the deterministic writing process, we have not so far seen quite such good coherence. We've seen examples of T2 spin coherence of a couple of hundred microseconds or so. The concentration of the nitrogen of the 2 parts per million is right on the shoulder of where you would expect to see the spins of the nitrogen starting to dominate the nuclear spins in terms of the decoherence. So we think we will probably see something slightly better when we work with lower concentration of nitrogen. But we think probably the main thing is that sample is not as homogeneous, and that there are perhaps other defects within the sample that are affecting the coherence times there. What we really don't see is as good optical transitions in that sample yet.
Okay, and so I think this was one of the related questions. What is the, because you've shown the inhomogeneous line width distribution for the first technique, but not for the second one. How does it look like? And do you have radiative lifetime limited line width in this sample as well, or not?
No, we don't in that sample, and that's because we think because of the high nitrogen concentration within that sample. As we know, the optically excited state is always perturbed a lot more by any sort of local inhomogeneities and things like that than the ground state is. So yeah, so we're working on trying to do the annealing process with lower nitrogen diamond now, and the main thing that we're having to do is to work with a laser which has a higher pulse repetition rate, because that 1 kilohertz pulse stream is a very, very slow process. You don't want to have to hit the diamond too hard. And so it really places a limitation on how far you can make the vacancies move before they find a nitrogen. So to work with the lower concentration of nitrogen, we need to go to a higher rep rate.
And the last question, maybe, actually it's a double question, and how close can you make the NV close to the surface? And the related question, I noticed that on the Z direction, the control of the position is not so good, like 200 nanometer. It's not as precise as in the XY. Is it a problem in the long term for insertion in an open cavity system, for instance?
Well, obviously, the how you go about building an open cavity system depends on how you do the fabrication process, right? So to answer the first question, we haven't worked very hard on trying to do the writing very close to surfaces. And I think there are approaches to doing that, such as using solid immersion lenses and things like that. But yes, clearly, if you try to write too close to the surface, you're going to get some damage occurring at the surface before you get the bulk effects, which you're looking for. But I think, yes, it's a question. If you want to integrate these into devices, then clearly you have to have a fabrication route that allows you to do that while still doing the fabrication a little bit below the surface.
So unless there is another question, I think we are a bit late. So thank you again, Jason.
Thank you very much, and thanks to the organizers for the invitation. It's been a pleasure.
Use laser annealing for SIV centers also.
I'm sorry?
Can we also use your laser annealing technique for SIV centers? Silicon.
We haven't tried the laser annealing technique yet for SIV centers. That's an interesting idea.
Okay. So we need to move on. Thank you again, Jason. It was nice to see you.